You might think that Earth is this wonderful Garden of Eden planet with all of the raw material required for life. But in fact, our planet is nutrient starved for the kinds of chemicals that are really required by life. And you know how amazing that life is by all of the incredible, clever things that it does to extract nitrogen out of the air, to pull phosphorus out of rocks, and to be able to do all kinds of really complex chemistry. And in the beginning, life didn't have a lot to work with, just the raw material, the lava that had spewed out onto the surface of the planet, the occasional meteorite strike. But maybe it had something else to work with, and that is dust, cosmic dust coming from space that might have just sort of smoothed off and provided an additional source of nutrients. My guest today is Dr. Craig R. Walton. He's the ETH Nomis Fellow at the Center for the Origin of Life at ETH Zurich and the Trinity College, University of Cambridge. And he has been proposing this idea that cosmic dust, which is falling to Earth all the time, you get about 100 tons of it a day, has built up in the right places on tops of glaciers, in glacier lakes, maybe other places where it provides a steady source of nutrients for life, especially in the earliest stages when life was trying to figure out how to, life. It got this steady stream of material from space, and that kick off all of life's processes to create this amazing biosphere that we see today. So enjoy this interview with Dr. Craig R. Walton. All right, Craig, I'm going to open this up with a zinger, so be prepared for a very tough question. What is dust?
What is dust? That is a good question. My work is on cosmic dust, which is a particular type of dust. And
yeah.
It has
I don't really care about the stuff that I find under the couch. I want to know about cosmic dust.
Exactly. So you asked what dust is, but we care about cosmic dust. And cosmic dust is literally just a size fraction of the particles that occur in the solar system. So the cosmic implies that it didn't come from Earth, and it's anything below 3 millimeters, I believe. And then if you get down to nanometers, then you're into nanocrystalline aggregates. So anything basically sub 3 millimeters, provided you're not looking at like a tiny little, accumulation of molecules, counts as a dust grain.
But what is it made out of?
Yeah, so it can be made out of lots of different things. So that's why the term cosmic dust in itself doesn't tell you a whole lot. You need to be more specific if you want to answer that question, like what's its composition. It can be made out of carbon, long-chain carbon molecules. It could be made out of ice, or it could be made out of silicates and iron. The vast majority of cosmic dust grains are made out of these silicate minerals. So that's where you have silicon and oxygen bounded to some cation like calcium, magnesium, or iron, some others. They make up the majority of minerals in Earth, majority of minerals in our crust, and probably the majority of minerals in the solar system. But there's also quite a lot of just raw iron out there, raw metals, native metals, where you have metallic bonds. And that's because they're from the cores of planets, basically, that have been destroyed. You're probably aware the Earth has an iron core, and most large objects in our solar system have the same thing. There are collisions which break these things apart and give us the tiny particles, and they're a right mixture of crusts, mantles, cores, and everything in between.
But when we, often, as a journalist, I use this gas and dust. Like I use these two words together all the time, talking about how astronomers see a supernova that is enriching its environment with gas and dust, that James Webb is an infrared observatory designed to look through gas and dust. So is that dust that James Webb is looking through into protoplanetary disks the same stuff? Silicates, maybe some iron, maybe some ices, particles smaller than 3 millimeters.
Yeah, it is. I mean, to be fair, because I'm an earth scientist and a cosmochemist working on actual samples that fall to Earth from the solar system, I would need to double check with an astronomer because they often redefine the same words. So when they use the word metals, they're not referring to metals. you refer to things that are just heavier than like hydrogen or something. So I would hesitate to say 100% yes, but broadly speaking, yes, the composition of those dust particles, however big they set the limit at, will be right across the compositional spectrum. There will be a lot more ices though, because they're not only looking, for example, at solar systems and protoplanetary disks and more mature systems. They're also looking at nebulas and star-forming regions where there is a lot of dust particles. And at those low temperatures, the volatile elements like hydrogen, nitrogen, carbon have all just condensed, and you have these ices. But yeah, they can retain from spectroscopy. They can get information, and they're increasingly with things like James Webb. In fact, I'm actually a co-eye on a proposal I can't discuss much about, but they want to get mineralogical information at a very sort of granular level. Not just to say, oh, there's some carbon out there, there's some silicates, but which minerals? What does that tell us about these systems we're looking at?
And so if there was a bucket of dust, of cosmic dust in front of me, and I just sort of put my hand in and I scooped it up and I was holding it,
yeah,
what would it be similar to something that maybe I am familiar with here on Earth?
Well, first of all, I'd tell you to put it down because you've just contaminated the very valuable.
Too late. Too late. I saw your box of dust. Just went for it, and now I'm
yeah. But your question
I'm letting it slip through my fingers. Yep.
You're saying how would it feel different, or how would it? Yeah,
actually... but we here on Earth, we experience lots of different kinds of minerals and geology and sand, and I'm just wondering, like, if I had a handful of this stuff, and I'd be like, oh, that looks kind of like beach sand, or it kind of looks like what would it look like? It looks like ash.
Yeah, so it wouldn't really look like anything you're familiar with, for the most part. It certainly wouldn't look like beach sand, because that's dominated by just almost pure quartz and feldspar, which are minerals that don't really occur anywhere other than Earth. That's not completely true, but certainly most meteorites are not dominated by these white, really silica-rich materials, or silicate-rich materials. You've got much more of these metals, as I say, and more unusual minerals, which occur in the Earth's mantle, but also more abundantly in the depths of planets which have been smashed apart. So in terms of what it would look like, have you ever seen the black sand beaches on Iceland?
Mm-hmm. Yes.
Okay. It'd be much more like, you might think that's what I've given you.
Oh, okay.
But then you might be like, oh, there's some weird stuff here, where it's full of green crystals and yellow crystals, from olivine and pyroxene, which perhaps haven't been through any terrestrial alteration yet. So, I mean, if we're talking about the good stuff, like fresh cosmic dust, which is what I'm more interested in, then I guess one of the key distinctions would be that it's been out in space, and the only thing that's gone wrong with it is it's fallen through the atmosphere. I mean, some people work on grains that have been sitting around on Earth for millions of years, but then you've lost a lot of the useful, pristine materials, and then it would just basically look like clay and rust, and there wouldn't be such a good, valuable bucket anymore. But that's what you would visualize, this black, small, finely grained material shining in the light.
Oh, that sounds really cool, actually. I can't wait. I'm sorry if you've got some samples that I get too close, I may just go like, oh, what's that?
I mean, the problem is getting enough, but yeah, it's hard to get.
Yeah, I'm sure. But there is a lot of this cosmic dust falling to Earth every day. I know it's like 100 tons or something like that, falling through the atmosphere every day. So of that quantity that's falling, what's the mix? Like, how much of that just came from the solar system, and how much do you think came from beyond?
Good questions. So we actually know very well that percentage, and it's a tiny percentage that comes from beyond the solar system specifically. Because what we find in meteorites and in cosmic dust occasionally is pre-solar grains. And it's all in the name. They're grains that are older than the sun, which is remarkable. Because almost, I'm used to, even as a geologist, being, when I first picked up meteorites back in 2016 for my research, and, the person showing them to me, a guy called Richard Greenwood at the Open University, he was like, this is older than the Earth. That was mind-blowing to me. It's older than 4.5 billion years. That's amazing. Pre-solar grains are way older than the sun and the Earth. And we know that this is the case through studying their chemistry. we can see that they're isotope compositions. That's one of the key ways we can trace the source of materials. Basically, everything in the solar system is derived from an overall solar composition, which is the ratio of elements. So if you look at a meteorite, they're basically very similar to the sun, just minus a lot of the hydrogen. And everything can just be extracted from that, building planets of all different types, building you. But what you share fundamentally is certain stable isotope compositions, which are the different masses of individual atoms of a given element, which record that it's all from the same source. We trace processes that have happened by looking at subtle variations in those isotope ratios, but the whole solar system basically has the same genetic blueprint. And these pre-solar grains are wacky. They're completely wild. There's no way to make them unless they formed, for example, in a supernova from a completely different type of star. And so it's interesting that they're there, and that tells us something about the mix of materials that must have gone into making our solar system and where our star came from 10 billion years ago.
It's almost like a snapshot in time of what the composition of the Milky Way was at different times in the geologic record of the Milky Way.
Yes, it's almost like, I don't know, the cosmic record or something, chemical record. But it is, and it has been changing. That's what's fascinating. We'll talk about this maybe at a different point, but as we've had different generations of stars, more heavy elements being formed, the potential to form rocky planets has increased, and the compositions have changed. And there's a big debate about whether or not the galaxy has become more or less hospitable for life over time. My bet would be more. We'll talk about that more in a bit. But just to go ahead. Yeah.
Well, I was going to say, like, I know I read a paper. Someone was saying that the Milky Way became habitable a couple of, like, maybe 2 billion years before the Earth formed. And I guess this is the source that you're able to look at the composition of the pre-solar grains and say, okay, now we're seeing enough of the kinds of elements and the kind of abundances that you would expect for life to be able to evolve on a planet that had large quantities of that in it.
I would say that it's definitely part of the story. It's not that the entirety of our chemical history of the Milky Way comes from these grains, because they are quite rare, and by definition, they can only really tell us about our local stellar evolution, going back through a lot of time, certainly, but not necessarily telling us about the whole formation of the galaxy and going right back, to the origin of the universe, where you can use telescopes to do that. And telescopes can tell you some chemical information. Right now, they can't tell you any isotopic information, because the variations in a spectra you would get from one isotope to another is very hard to get at, but certain elements definitely. And you can see by looking further and further away, different types of stars, those chemical trends, and people are starting to piece it all together. But yeah, cosmic grains, it's nice because they encode it in a sample. We know it's not some kind of bias in our measurement or distorted through a telescope lens. We can put it under a microscope and under a mass spectrometer and say, yes, our predictions are true in some cases.
I find that so interesting that it's like astronomers are really trying to scan the sky with more and more powerful telescopes. They're looking to other star systems, and yet this material is being delivered directly to Earth, passing through the atmosphere, protected inside meteorites, and a geologist can crack it open, find the pre-solar grains, and examine them. Like, you don't even need a sample return mission. The universe is just doing this all the time for us.
Exactly.
You know where to look.
And not to knock sample return missions, or I won't be, making any friends, because we need more and more funding in space science. In my opinion, it drives the whole world forward and always has. But that is basically my bet as a scientist, as a meteorite person, is that the solar system is just giving us a lot of its best stuff for free, and it's built up in a minute. So when I started my PhD, for example, I finished now, but I got a lot of my samples from museums. You don't even have to hike out to Antarctica, where that would be a good place to go and get stuff. That works. But an easier thing than Antarctica is just go to the Natural History Museum, and they've collected amazing samples from across the last 300 years, a lot of which have not been looked at so much, because once a sample's sat in a box for a long time, people kind of just forget about it and they're not as excited. And people are always more excited by what's just arrived. So the sample that kicked off my whole career really was Chelyabinsk. I don't know if you heard of this one in Russia, 2013.
Yeah, of course. Yeah, I have a piece of it as well.
Oh, wow. Yeah, good work. It's my favorite rock, I think, ever. And yeah, it caught everybody's imagination because it was so dramatic. Falling as a fireball, exploding in an airburst, recording all those Russian dash cams. And so there was a bunch of excitement for a couple of years just because, oh, wow, what a dramatic thing. But for me, the actual rock itself told me lots of fascinating things, unlocking a whole part of my research in terms of decoding what these rocks tell us about stuff that happened 4.5 billion years ago, not just the fact of their arrival. But yes, the archive of material that falls to Earth is absolutely spectacular. And there's a lot we still don't know. But we need to supplement it with these sample return missions because the inherent problem of it being randomly sampled and falling to Earth is I don't know where it came from. I don't know which asteroid it came from, and I don't know the context of the rock. No geologist, like if I just gave them a random rock and I was like, figure out the whole history of the Earth from this, they'd just look at me like, well, no, tell me where it came from. I'll go look at where it came from, and then I'll figure out, so that is the problem. You need both.
All right, so I'd like to talk about your recent paper and what triggered my call to you, okay. And that is this idea that this cosmic dust has been, as I said, 100 tons a day, but you add that up for millions, maybe even billions of years, and that starts to turn into substantial amounts of material that is being deposited onto the surface of the planet. So, what role do you think this cosmic dust has had on the early evolution of the Earth?
That's a good question. So there's two possible ways it could have had an impact. Because, the reason I'm interested in it, in the paper that you spotted, that I had out recently, is in the context of the origins of life.
Mm-hmm. Yeah. So, yeah. I'd be interested to sort of think like geologically,
yes,
but also in terms of life, for sure.
No, let's go through it all. Yeah, there's different ways to think about this. So the initial reason that I got interested in cosmic dust in this context is that it has an anomalous composition compared to the planet. So meteorites in general, anything extraterrestrial, the reason it's obvious when it lands is because it hasn't been through the same processes that have occurred on Earth. So it really depends what the source is, but broadly speaking, Earth's surface is deficient in a lot of the elements needed for life. Okay, so your carbon, nitrogen, phosphorus, sulfur, iron, various processes have either removed it and ejected it into space, or extracted it from the surface and buried it underground, or put it deep into the mantle or even the core. And there are some materials out there which haven't been through that process. Asteroids which never experience forming part of planets, and quite a lot of the dust does actually come from those objects. So I became interested in it from the perspective of, okay, perhaps this is like a fertilizer when it was arriving on Earth early on that would have given life a bit of a kickstart. Because today life has all these incredible processes to deal with how essentially fundamentally inhospitable the Earth is. They have enzymes which can overcome kinetic barriers and extract nutrients from the environment, even if they're vanishingly rare. Early on, before you have enzymes, you don't have that. And actually, if you go right back to the start of the field of origins of life, people immediately suggested, like people like Alexander Oparin in the early 1900s were talking about meteorites because they already knew they came from space, they were enriched in the elements that life uses, and they made that possible connection. And in terms of what dust can do to the whole planet, it's not just as this possible fertilizer. Dust in the atmosphere is very effective at cooling the planet down by reflecting light. So if you have a huge quantity of dust arriving on the planet in the atmosphere, there may be climate effects that people have thought about from a cosmic dust perspective, but only very recently. So the example would be that several papers looking at a mass extinction that happened on Earth about 460 million years ago during a global ice age. Global is a controversial word, but a big ice age caused a huge extinction. It's probably not the most famous one. Probably, end Cretaceous, end of the killing of the dinosaurs, also extraterrestrial in origin, probably. But the fact that this ice age happened was always a bit strange in the geological record. It just sort of happens like this. What happens at roughly the same time is there are rocks full of cosmic dust, like full of cosmic dust compared to background. And it's been linked through some of my work and other people's work that a giant asteroid collision took place around this time, probably just randomly out in space, generating huge amounts of dust that arrived at the Earth, cooling it down, plunging the planet into an unexpected ice age, which life struggled to deal with in time, and it caused a mass extinction. So that's what one way it can have an impact. And just to sort of round off these implications, I would say that in general, delivery of extraterrestrial material is fundamental to shaping the Earth we have today. Probably. We know that a huge amount of material arrived in the first 500 million years from space, because the rocks that we have in the crust are way more enriched in certain volatile and siderophile elements. So that's iron-loving elements that should have ended up in the core. So if this hadn't happened, we'd be struggling to build mobile phones and power a lot of our technology, because the process of core formation extracts those elements which are, when we value them and call them rare, they're not actually rare in the solar system. They're not rare in many meteorites or in cosmic dust. They're just rare because of the processes that Earth went through. But I would just, it's irrelevant to mention that, because it's the delivery of those elements is crucial for, as I say, forming the Earth as we know it. But most of it wasn't delivered by dust. Most of it would be delivered by big objects. Dust is in a way, the rarest, the least massive contributor overall, but it's the most reliable. It arrives in the highest quantity per year, but then every now and then you'll have a big thing comes in that just delivers way more. But it's all at once. And if you're interested in the origins of life, that it's a bit like the example I always give is if we sat down and had an amazing meal right now, like a feast for the ages, but then I never fed you again, it's no good. You're going to die. You need something reliable. And that's why in trying to think of ways to improve upon the age-old meteorite origin of life idea, I think cosmic dust may have some advantages.
Right. And so let's talk about that idea of, I mean, you made this sort of throwaway comment a little earlier there that Earth is, I forget the word you use, inhospitable. Like Earth is marginal at best, right? Are you saying like today, even now, the surface of the Earth is, and that life has had to get really clever about how it's able to use the
life is
the empty shelves that the Earth has left it with?
Yeah, I mean, like the Earth is certainly better compared to like the Moon, because we have an atmosphere and liquid water. And people think, oh, liquid water, life. But that probably isn't true. There's probably like a whole bunch of other things that you need to get going, because if you think about what life is doing right now to power the huge amount of biology that exists, it's doing some amazing things. Phosphorus is one. That's one thing that I thought about a lot. In fact, I'm wearing a weird trinket right now, which has the old alchemy symbol for phosphorus on it. It's my favorite element. It's a key element for life. We know of no life that doesn't involve phosphorus, and it plays roles in forming the cell wall, making sure that DNA doesn't break down, and powering metabolism. So that's always my pitch for why we care about phosphorus. But phosphorus is rare. Phosphorus is rare on the planet. Like if I sprinkle a bunch of phosphate fertilizer into any given environment, chances are you'll suddenly have life blooming there in higher abundance than before. And our whole civilization, actually, humanity, is currently just rapidly extracting phosphate rock from a couple of places on the Earth where it happens to be in high abundances. And if war were to break out in all of those places at once, we'd be faced with a global famine in no time. So we ourselves have been maybe not clever enough, but somewhat clever in finding ways to extract these resources. And for example, life right now does this amazing thing where a bunch of phosphorus gets used by life. Organisms die largely in the oceans and sink to the bottom. And if that phosphorus wasn't taken back out again of the dead things, you would just run out. You'd run out. You'd be source limited because it's not very much at the surface. What life does is it breaks the biomass down, extracts the phosphorus preferentially, and that upwells in these nutrient-rich water columns. And it's like 99.9% of all phosphorus used by life each year comes back out in this big conveyor belt. And life had to evolve this. So many people think that before life had come up with this recycling mechanism, there would be less life on the planet. And that goes right the way back to the origins of life, where we were trying to come up, and it's basically an unsolved problem. Which environments had enough phosphorus just sitting around for these reactions to get going before you had any way to recycle. It's like a chicken and egg problem. And cosmic dust is one potential reservoir of this fertilizer, where it's a very reactive source. And it is basically, I keep using the word fertilizer, but I think it's analogous. Because if I gave you a big rock to fertilize your garden, you'd just look at me like, thanks, not very helpful. But if I give you a powder, or even better, a liquid fertilizer, then it's going to work tomorrow. So where was I going with that? And another example of how life and the planet is not very conducive to life, but life finds a way, is nitrogen. And the other key fertilizer. Humans have also developed amazing ways to extract, to fix nitrogen. So to take us from an inorganic to an organic form, and then fertilize our plants with it and make food. And life does this. Life goes from N2, which is an incredibly robust molecule making up most of the atmosphere, and splitting it apart and making organic nitrogen via the power of the nitrogenase enzyme. And that is like a masterwork. It's a masterwork. And especially for oxygenic photosynthesis, there's a whole problem there as well, where the process releases oxygen, which inhibits the nitrogen fixing enzymes. So life has had to come up with not only a way to produce all this energy, but then to save itself from the toxic products that the process produces. And so life has had to go through jumping through all these hoops. And it makes sense that natural selection over billions of years can come up with some way to do this. But if you go right back to the start, where none of this is operable, it's hellish. It's like, and that's why it's a difficult problem to solve. You just have basic chemistry that's stupid, and it's like, how is it going to figure it out?
Right. That is really interesting. I think we sort of imagine the early Earth as some kind of primordial garden, that all of the raw elements that were needed for life were sitting around in warm pools with lightning strikes and black smoking volcanic vents at the bottom of the ocean. And life was able to start almost anywhere. And yet, as you described, when you think about all of the tricks that life has had to come up with to just survive on this inhospitable planet that just doesn't have enough of the stuff that it needs, it's astounding that life got started at all.
It is astounding, which is, I think, why people have all sorts of different views on it. I regularly get emails from people who are like, why are you even working on this? Like, clearly it was just divine intervention. Like, there's no other way, because it's impossible.
Because that's not an answer. That doesn't help.
It's not an answer, but like often the criticisms of like the problems are real, but I'm convinced there's a resolution. And so I have several thoughts on this. One of which is
sure, go ahead. Yeah.
I was going to say, maybe one of the things we should talk about is the overall landscape of work into the origins of life and deep sea vents versus the land, and why I'm thinking about dust versus other things.
Well, the only thing that I wanted to do was just finish up the conversation just about the dust and about how the glaciers serve to concentrate the dust, the mechanisms that we get this concentration, which I found really interesting.
Yes. So to get there, I'll just say that in response to the vision we have of the early Earth is like a Garden of Eden, that's almost certainly not true, but it must have been true somewhere. That's my perspective, is that somewhere at some point on the Earth, in a way that wasn't a miracle, there was just this accumulation of all the things needed to get life going. I don't think it was global. I think most environments on Earth were probably horrible for origin of life chemistry. And I would have big criticisms of the ocean on that case, because they're so dilute. Like life in the oceans today, as I say, has all these problems it has to face. And I can't think of a worse place to concentrate the elements of life, because it's completely diluted in almost infinite amounts of water. That's why Darwin's idea of warm little ponds is attractive, because the volume of water is very small. You don't have to add very much to it to get it concentrated and then make the reactions favorable. And so that's linking to what you just mentioned in the paper. We talk about concentration mechanisms. So cosmic dust on its own, there is quite a lot falling to Earth, but it's not like the world's most pressing thing. Like, you don't walk outside and think, oh, there's a lot of cosmic dust coming down today. It's quite hard to find. And it's because it's distributed over the whole surface of the planet. It is slightly more easy to find than people thought, because just in the last 10 years or so, people have realized that if you just go onto the top of old buildings, you can find some. And this was like a ridiculous idea for a while. And I think it was bizarrely a Norwegian jazz musician who pushed the idea. And after like decades of knocking on doors and asking people to look at his samples, people realized, oh, he's right. You can basically just filter through the trash on top of whatever your local, ancient city hall, and you'll find like a few bits of cosmic dust. But it's not enough. And people had previously thought, oh, it's not relevant for origin of life, because even though it's sort of global and reliable, it's not enough. But the Earth loves to concentrate things as much as it does to diffuse things. And so in the top of ice sheets in particular, one, you have no competition from other sources of sediment, right? It's mostly ice. All the erosion's happening at the bottom. And two, if you do have these particles raining out all across the ice, they'll get randomly moved around by the wind. And then if they hit a spot where they can't move anymore, they just start to accumulate. And so that's where people go to find the meteorites and cosmic dust, is these locations: blue ice fields, and for cosmic dust, cryoconite holes. It's a weird word, but it means this icy sediment. And it's where you have just randomly even slight enrichment of these dark particles of dust, some of it cosmic, some of it not. And it heats up compared to the ice. It melts a little hole, and then more dust accumulates, and it gets bigger, and it melts down and forms this column of liquid water and fertilizer. And it's an oasis for life in an otherwise totally inhospitable environment. And you get lots of microbes, weird and wacky ones. And these are some of the most radioactive natural ecosystems on the planet, because the dust is full of radioactive elements. So it's a really interesting microcosm that develops in this place. And it's where dust is like 10,000 times enriched compared to what it would be otherwise. And in our paper, we basically ran back the clock, using all of the knowledge that we have from astrophysics and geology of how much more was coming in. And if you do that, you end up saying 95% by mass of the sediment back in the day, if there were ice sheets on Earth, would have been cosmic dust. And that is very exciting.
And so this is like after the glacier has melted away, you're left with a sediment.
No, it's there at the time. If you go to the top of the glacier, you'll find these large, black, weird deposits, which are half frozen, half molten. And yeah, they're there right now, but they're unstable. So on the course of decades, because they tend to form near the margins, they will tend to be drained away and removed, and all the material ends up getting dumped into what are called proglacial lakes. And so having sort of shown that this is an interesting thing to think about, one thing I'm collaborating on with my glaciology friends is thinking, do we care more about the initial concentration mechanism, the cryoconite, or the proglacial lakes where everything ultimately ends up, or both? Like, which is the better environment for doing the chemistry, or if any chemistry is going to happen from this type of system?
So just to understand, so like this material is coming off of the glacier, going into, it's being collected into lakes and maybe forming sediments at the bottoms of these lakes that you could then, and I'm sure like so much sedimentary analysis has been done in these glacier lakes. Must be a pretty hot field of study already.
Yeah, for sure. I mean, people love to study glacial lakes and the layers of sediment for climate change reasons, and in general, areas with lots of ice and sedimentary systems is great for thinking about the Earth over time, because you sort of know what's going on. I mean, yes, I'm talking about there's some microbes there, but there's not usually lots of animals mixing everything up and moving it around, and you don't have massive seasonal variations that just mess everything up. So yeah, there's a lot of work that's done there to tap into. Unfortunately, not all of it focuses on cosmic dust, because I think this newfound relevance to the questions like origin of life is like a bit unexpected. So people maybe haven't worried about it so much in the sense that, like, okay, it's rich in cosmic dust, but do we care about that? But hopefully,
you're like, I care.
Okay, great. Yeah, now we care.
Right.
Now we care. So maybe we can, in a way, go back to all that literature and use it to tell us things that it wasn't initially measured, with that in mind.
And so what role do you think this played into this idea of abiogenesis?
So I've already given the pitch of the fact that the Earth's surface is usually deficient in all these things we would need. It's easy to get water. It's easy to get light if you care about light. Sometimes light is used in the lab to drive some interesting, potentially prebiotic reactions. But you're going to be lacking nitrogen, carbon, sulfur, iron, and phosphorus, among other things. Cosmic dust has all of them. And so the way I see it, potentially, is you have this fine-grained material that is like your fertilizer. It's like a battery. You can imagine, this is a paper, a follow-up paper I'm working on at the moment. I want to test theoretically and experimentally how good it could be. Imagine you have a reservoir of the element you care about, and you're relying on this to synthesize all the molecules of what will become the first cell. Say it's phosphorus. If I just build up a whole lot, and I don't have any stockpile in reserve, your reactions will start off quick when there's lots and lots and lots of phosphorus going to whatever, lipids, DNA, ATP. And as it runs out, you're going to get clever very quickly. You basically put all the emphasis on the first stages of life to invent these recycling mechanisms immediately, before that runs out. Or you can couple it to a supply. So say we put some cosmic dust at the bottom. It's very ready to dissolve. As soon as the concentration of phosphorus starts to go down as it's being used, you'll start to dissolve more out of the supply. And that wouldn't be true of most places on Earth, because you'd have these rocks, not so much phosphorus in it, not in the right format. I mean, I'm not saying that there's no terrestrial way to do this. I mean, I'm being quite bold here with my cosmic dust idea. But it would definitely not just be able to do this for phosphorus, but also potentially for, as I say, sulfur, carbon, nitrogen. Anything you start to run out of, you just take more out. That's how solubility laws often work. So it can be like a battery, where as your laptop runs low, you get more juice out of the socket in the wall. And I think that's potentially a really critical problem in origin of life sciences, not just which reactions, but how do we get a source that's coupled to the demand. So that's roughly how I envisage it. The problem really is whether or not the reactions that would lead to life would actually happen. So I mean, I don't want to destroy my own argument immediately, but there are some pretty obvious pitfalls which sort of everybody has to contend with whenever you start from anything geological. Is that rocks aren't very reactive on the whole, and even in cosmic dust, which is pretty reactive, the carbon, right? That's critical for life. The carbon in those grains is largely in a form called polyhydrogen cyanide. And it's really insoluble. And a lot of the other forms that are in there are also insoluble. So you would need to come up with a way to activate it and make it reactive. If you're just putting it in water for the carbon, it might not be enough. And so you may have to think about shining ultraviolet light on it, which can break it down. And nowadays, that would give you cancer. But for the origin of life, that might not be so much of a problem. You might be more interested in breaking things down, getting them reactive, would
that need to happen in water, or could that happen in the upper atmosphere? Could that be happening in space?
Good point. It can definitely happen in water. In the upper parts of water, the UV light, because there was a lot more UV light, you see, back on early Earth. The sun was emitting more of that stuff, even though it was less luminous overall, and the atmosphere had no ozone, so it was reaching the surface. So it definitely can happen in water. And the problem with it happening in space is that it won't penetrate through rock. So the very, 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 very outermost stuff might have some interesting space weathering photochemistry. But it's really when you put it in water and you start to get this stuff into solution that the interesting chemistry will happen.
But I mean, we think about the various carbon molecules that have been found in the atmospheres of places like Titan. They're finding methane, ethane, acetylene, all of these sorts of things. And we know that water was delivered to Earth later on, maybe by comets, maybe by asteroids, maybe by dust grains is another sort of theory right now. Couldn't you also get those carbon molecules being delivered at the same time in a more useful form than bound up with cyanide?
Sure. You mean, so could there be other sources of carbon on the Earth, and could some of it be
Yeah.
experiment? Yeah, definitely. I mean, like,
Yeah.
this is just one idea, and the reason I find it interesting is because it, as I say, it's reliable, and you get a lot from one thing. You get lots of elements, but there's definitely potentially more impressive and larger sources of carbon specifically. So you can get some reduced carbon species. Reduced just speaks to the oxidation state. So rather than being bound to oxygen, maybe you're bound to hydrogen instead. And that's the molecules of life are all reduced carbon. Coming out of the mantle directly from processes like water interacting at high temperature with the mantle. This is like black smokers and deep sea hydrothermal vents, which have long been thought about in the origin of life community. You can get some of this coming out there. People do work a lot on photochemistry in the atmosphere, just starting from CO2, and it's really hard to go to these organic hazes, like you say, occur on Titan. On Earth, it's quite an oxidized planet, even before we have atmospheric oxygen, O2. There's a lot of oxygen around, lots of CO2, and so people invoke things which might be possible, but are a little bit arbitrary, like you change the oxidation state of the whole atmosphere by delivering a massive iron asteroid, and it vaporizes and turns all your CO2 to methane, and then great, then you can start to make more interesting things from that. So there are other ideas, but then even if you've made it in the atmosphere, you still face the problem of putting it into your pond and concentrating it. So it would be very nice if you could just start from one universal feedstock and do everything from that, but that might be too simplified, and you may have to draw in, and even that could even work with cosmic dust. Maybe you get your phosphorus, nitrogen, sulfur, iron, blah 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 from dust, and then just are importing by diffusion from the atmosphere other things after one of these big impactors.
I like that idea that there is some sort of ratio of carbon to potassium to nitrogen, whatever, in this dust. And that I've sort of imagined video games that I've played where you're trying to manufacture, like Factorio, and you're trying to manufacture something. And eventually the speed that you're able to pump out new components is limited by whatever is the thing that you have the least of, but you still get to make them. Like, even though it might be the rate is not enough to stop the bug swarm, you are still able to produce some. And so on Earth, as you said, if you've got a constant replenishing of this material going into this warm little pond, then it might take longer, but at least it's not going to the fire will never completely go out.
Exactly. And that's basically, in a way, that analogy just describes life on Earth, right? Like the inputs are small for certain key things, but they're not zero. And life is able to amplify that and make very efficient use of it. And the real question for origin of life is just, how do these reactions work? How efficient are they? What is enough? What counts as enough? Because it's not enough just to have like one molecule of, for example, not poly, but just hydrogen cyanide. A lot of people work on starting with that. Is very reactive. And you can make, basically you can take it all the way through to the foundations of cell walls, the genetic code and metabolism, just with a few bells and whistles added. If you just have one molecule going to another one molecule every million years, clearly you'll never get anywhere. And one of the problems with having a very limited production rate is that there's lots of sort of small deaths that happen and add up in a chemical network where molecules go the wrong way randomly. You produce side products you didn't care about, especially without enzymes to control everything. And then the products, even if you've made the thing you want, it doesn't last forever. So in video games, oftentimes you're trying to replenish your health bar, right? It's like in The Sims, if you just leave them alone for ages, then things won't go well. And it's the same is true. You're trying to sort of maximize all these different things that can then interact together. But entropy and the environment is often working against you, and trying to just create chaos and destroy the things you've made before you can do anything with them. So you kind of want a continuous and a large source. The problem really for us is performing experiments that truly tell you what that would be is hard. And I think we're entering a new era at the moment of not just theory, but experiments where people are coupling the interesting organic chemistry that's been discovered that seems relevant to the origins of life to realistic geological scenarios. I mean, at the beginning, for maybe 30 years ago, the scenarios were a bit unconnected, and the two things were just in different worlds, and each would criticize the other. The geologist would say you're not using geologically relevant things, and the chemist would say your scenarios don't do anything useful for the origins of life. And now it's converging. Now there's some interesting data points where we're iterating. And for example, I'm going to keep going back to phosphorus, but the people who came up with a lot of the hydrogen cyanide stuff that's been publishing in top journals for a lot of last decade or so in Cambridge, John Sutherland, Matt Powner, Dougal Ritson, and others, they added phosphorus en masse one day to one of their experiments, and suddenly everything just worked amazingly well. And if you were just naively going from biology and saying, oh, we need lots of phosphorus, the fact that it helped reactions that it wasn't even participating in, it catalyzed and buffered and eliminated all these horrible side products. Immediately you start to think, oh, high concentrations of phosphorus, which is what you might naively want and think you would need, it helped things that you weren't even initially trying to do. Which environment would have that? And then when you go to that environment and you start to say, well, what else occurs there? Feed that back into the experiment works even better. And you start to think maybe we're going down a path here which is leading us through a process of trial and error to the holy grail, the environment where this did actually happen. And it's not got there quite yet, because I think that level of collaboration is only just emerging and it's a bit random at times. But I'd give it 30 years, I think, maybe much earlier than that. Somebody at some point will just produce the right environment and the right processes in the lab, and they'll make something like life. That's my thought.
That's your prediction. That's pretty great. So I'd like to shift gears then and talk about what the implications are there for life across the universe. I sort of think about other worlds where life could try to get started, and maybe some really unfortunate folks, like people who are on, say, ocean worlds, where they, how do they get access to nutrients? Do you think that dust can save the day?
Not on an ocean world. No way in hell, because it's just going to be diluted so much. It's like pouring a tea bag into the ocean. And that's not going to be I'm drinking some tea right now. I've not added loads of water to it, because then it'd be too dilute and it wouldn't be any good. So the thing is, I don't want to necessarily rule out that there's life on an ocean world, because it's always too arrogant with these scenarios to say that I know for certain anything. I don't. We need to put a lot more evidence one way or the other. But just working with the thought experiment that it's these really local environments that are crucial for getting you over the barriers and on the path to life, I would say that the majority of planets that have liquid water at their surface may be habitable but not inhabited. I would imagine that's one possible resolution to this thing that we don't observe. There's loads of habitable planets out there that have civilizations already. We can talk about that more in a minute, but I would imagine, for example, these ocean worlds, which seem that they might be quite abundant potentially. James Webb will tell us more on future missions. If they don't have any of those spots that are thermodynamically and kinetically favored for that little bridge that gets you into biochemistry, even if I was to put a cell on that planet and it would colonize the whole thing, if you can't get to a cell, not going to happen. It will be uninhabited. So I would say cosmic dust will only work on a planet where the geology can make use of it. And it may even be that is not the solution. I have to say that. It may well be not. But I think that the general principles apply where local environments that can concentrate all the things you need to be able to form.
But so if you have an ice flow and dust is falling onto the ice and then concentrating in those little divots, then maybe there's a shot.
For sure. Say part of the planet freezes in the north. Say it's a tidally locked planet and one side of the planet has ice and then the dust builds up there. But then it just depends. Like, what if the intersection of ultraviolet light with dust is what was crucial? Then maybe a tidally locked planet where the ice is on the wrong side won't. It just depends. Like, there's so much we don't know. But I would make the case that it's not just even the origin process itself, the origin setting, but so many things going in to build the planet to make it possible to host life. I think that Earth, despite not still being like that easy, it ticks the boxes. And I think lots of other planets that are nearly good enough will fall short. And there's so many reasons I could think of for that.
But
I could give some.
To defend you, it really does feel that what you're identifying is this error correcting capability of dust, that no matter how bad this planet is, there's going to be a constant stream of material that is incredibly rich in the kinds of minerals and atoms that life is going to need to get going. And so if its planetary shelves are bare, there's still this trickle of dust, and who knows what kinds of shenanigans life can get up to over billions of years with this regular input. So
I think what I would add
that's the impression that I'm getting from what you're describing, is that dust smooths off the rough edges and provides an input that makes planets that would normally not be habitable, now there's a chance.
I mean, that's the implication, certainly. Like, if it turns out that cosmic dust was the magic sprinkle that got everything going, then Earth without that would not have life. That would be a logical inference. Mm-hmm. So your statement would be true if that's true. And I just would add to that the nice thing about it is it removes the element of chance. Like, if this is enough under quite climate conditions to get you life, then it doesn't rely on a meteorite hitting the exact right pond at the exact right time immediately after the atmosphere was reduced and blah, blah, blah. It's falling everywhere. And then wherever you then have the process to concentrate it, you're guaranteed to have the dust falling. So yeah, it would make it sort of inevitable rather than sort of 1 in a million that would happen. The 1 in a million part would then be the planet itself. It'd be a planet forming the right distance from the sun with the right atmospheric thickness, not to boil or freeze. And there's all sorts of other things that people are thinking about now that we're observing other planets, that Earth's probably in a sort of Goldilocks zone, not just in terms of you've probably heard of the Goldilocks zone, right? Of like stellar distance from the sun. You know, if we move the Earth either way, we'll be like freezing cold or end up like Venus. But there's probably also compositional Goldilocks zones in the chemistry, which mean that even if we did everything like we did on Earth in a different solar system, you still wouldn't be able to have life. And that might be what we talked about earlier, right? This like cosmic chemical evolution, where the concentrations of elements needed for life were too low. And it might also be the way in which planets form. So I mentioned earlier that core formation extracts certain elements. It's extracted most of the phosphorus. That's where most of it's gone, is to the core, because it likes to go into iron. But there's under other conditions, like just set by the overall chemistry of the whole solar system we're talking about, it can flip, and the core hates phosphorus now, and it just builds up in the crust en masse. But what's interesting is if you start doing that, it turns out that nitrogen under those conditions starts to behave like phosphorus, and it goes into the core. And you can plot these graphs. This is another paper I'll have coming out at some point, where it's basically as a function of how much oxygen exists in the planet. You'll either have no phosphorus at the surface or no nitrogen. And it just so happens when I put Earth onto this graph, Earth sits right at the crossover point where you have both in non-trivial amounts at the surface.
And that wouldn't have happened if it wasn't for life.
No, sorry, maybe I've explained it badly. I think that makes life possible.
Okay. So life isn't driving those concentrations to this crossover point.
No. The implication is that the fundamental composition of the solar system, just set by whatever it inherited, right, its inheritance basically, determines what's then going to happen when you form a planet. And there's this very narrow window where you can have the elements needed for life at once. And so the implication is probably most planets are really deficient in one or the other. Even if they have liquid water, they'll have no nitrogen or no phosphorus.
So what implication do you think that has for searching for biosignatures?
That's a really good question. It's something I'm getting more interested in terms of applying these thoughts to. I mean, at the end of the day, all it can give you is predictions. Like James Webb will find what it finds. Future telescopes will find what they find, and we could be wrong. We're just extrapolate based on our theory and our experiments. But the one implication would be that Earth may be rarer than it seems. There might be plenty of vaguely Earth-like planets, but specifically Earth-like planets that tick all these hundreds of boxes might be quite rare. And especially if the number of Earth-like planets being born has increased over time. One point I would just like to make on this show, which I think people should think about, and I'd be interested to hear a debate about this at some point, is that Earth might be one of the oldest truly, Earth-like planets that exist. There might be loads of others that are quite Earth-like, but much younger. And so, especially if we're talking about really, really obvious biosignatures like communications from a civilization, if we just naively say everything's going to be the same as it was in Earth history, it takes 4.5 billion years to make sentient things that can communicate, that might make Earth the oldest and only planet that's reached that point yet. So it might be that we have a fair number, maybe 100 Milky Way neighbors out there that will get here, but they're 1 billion years away. And so that would be one sort of non-pessimistic resolution to the whole Fermi paradox.
So that's it? That's your resolution to the Fermi paradox? You did it?
My personal view is we are the first, and we have a couple of neighbors out there which have life right now at various stages, and have had various amounts of time to sort of figure this out. But evolution is kind of semi-random, or it is random, but then natural selection makes use of mutations. It probably won't take an order of magnitude shorter or longer to get to similar complex organisms. I think we're alone because we're the first, and we have a lot of responsibility because of that. But I don't think it's because lots and lots and lots of planets reached this point and then they all died as soon as they became intelligent. I mean, I'm not that pessimistic. I think we'll be fine. I think the real danger to all these other inhabited planets is that we'll eventually go there and just replace them with our own, biology, because they're too slow races.
Right.
That's what I think. But maybe they're far enough away. Yeah.
I mean, I agree with you that the only resolution that makes sense to the Fermi paradox to me is that we're first or we're alone. It sounds like you don't like the idea that we're alone. Who does? But then I can send you the paper if you want that says that the conditions for life were probably around about 2 billion years before the solar system formed. So we can't be first. If this process takes about 4.5 billion years, there are planets that did that 2 billion years ago. And where is everybody?
Good point. I guess I would need to know what their criteria, though, because given that nobody's made life in the lab yet, I would immediately respond to them and say they don't know what the conditions necessary for life really are.
Of course. But just in terms of the concentrations of the kinds of elements that are required for life, that you need enough supernova, you need enough material going off that's concentrating in solar nebulae to the point that terrestrial planets can form with the kinds of abundances of chemicals that we see today.
Do you remember? Well, I think I'd need to read the paper.
I'll send you the paper after we talk.
Do that. I mean, I'd happily have a round 2 where I respond to that, because I am surprised that they'd be able to make that claim. To be honest, because it wouldn't. I mean, the conditions necessary for life. What we're talking about here is as if we're just going to go off the basis that it has to be like Earth. I mean, maybe it's possible to make life on a planet that's not like Earth, but I'm not interested in considering that because I don't know what that would look like. Anchoring it to Earth scientifically makes the most sense because we know it's possible here. You're wanting the same type of star. You're wanting the same size of planet. You're wanting the same overall composition of the solar system so that core formation goes the same way. And other things that seem really fundamental to what's happened on our planet that might not be reproducible include things like the moon forming impact, which may have been semi-random. And so if you add in these sorts of really major events, I still think that even if it's possible that Earth-like planets may have first started forming 2 billion years earlier than ours, it would still be very possible that we were the first to have life develop. I'd be curious to think about the statistics here. It's not where the direction I've fully taken my research yet. It's quantifying this, because there's always so many unknowns that Drake equation, statistical approaches, and making very firm statements are kind of hard to be confident in.
At a certain point, though, the Drake equation just becomes worthless. The last couple of numbers on the Drake equation are of no help at all. And you could absolutely add 10,000 additional parameters to the Drake equation, but you're still going to end up with 2 at the end that tell you how often life forms. I don't know. So we just can't know. But I do wonder if, back to that idea of the solar system grains, and I wonder if you can get a sense. There's an idea that I really like, that the moon is the perfect place to go and do a core sample to see the history of the universe, that you core down into the moon and you get every supernova, every stellar flare, every interesting asteroid collision that happened in the solar system throughout the moon's history, as long as you can make sense out of the regolith. And I wonder if you could go back in time and see and watch changes in those interstellar grains and say, oh, actually, it looks like interstellar geology has been changing over time at this rate, and that we can predict when the Milky Way was properly habitable.
It's an interesting
so we need to go to the moon
point. I mean, I think I would refer back to the point that we can do a version of that very nicely with our telescopes. We can basically time travel using telescopes by looking at stars that are at different ages or different distances, and therefore further back in time. And we've learned quite a lot from that, although it's still unsettled, hence why we're having this discussion.
Right, but you're not getting a sample of the moon. You're not getting a sample of the dirt that came out of that.
I do agree. There's a lot we can learn there, but I think picking out there's several things to account for there. One of which is that our position in the Milky Way is not fixed, and we move through different areas, and interstellar objects fly through our solar system. So if you could, in principle, extract like the signal of where we were and when it was, that would be incredible. But I think it sounds quite tricky. it sounds pretty hard.
Tricky work. I get that.
But what I would say is just very adjacent to that is people are interested in finding the oldest rocks on the moon and trying to find ejecta from the Earth, from impacts on Earth that sent it to the moon, because the moon's surface hasn't really been altered very much. That would make it this sort of geoarchaeology. And so it would be interesting if we could survey the whole moon's surface, if we could find any rocks that were ejected from Earth at the time of the origin of life. Because on Earth, we can't go past 4 billion.
Right.
That critical period of time.
I was going to say, we do know the Apollo samples have some samples of Earth that were found on the moon. But no. I'll send you that paper too if you like.
This might be Josh Snape's work, or maybe I got the name wrong, where they claim they'd found Earth zircon. But I think that's incredibly controversial. It's certainly not settled.
Is it? I didn't realize it was so controversial. Okay.
Yeah. It is. I mean, most of these papers don't seem controversial when you just read them. Oh, cool. But I think people have major...
right.
Yeah. Certainly we never found a rock. At the very best, it's like
grains inside another rock that were mixed up in the regolith from some impact.
But just to finish... sorry.
But a more comprehensive search of rocks on the surface of the moon to look for material. Like eventually one will pop up if you do a better job of that.
And that would be great. Because, as I was just saying, like, on Earth, erosion, subduction, plate tectonics has destroyed the critical period of geology where we would just be able to look at rocks and find out. I mean, the reason this is also mysterious is because we don't have evidence. We can go back to this event horizon 4 billion years ago at which the rocks run out. Everything older has been destroyed. That's not true on the moon, and that's why you might be able to go and find something that was displaced there and get a key piece of insight. So it's very unfortunate, because otherwise this would be an easy question.
Yeah. Craig, what are you obsessed with?
What am I obsessed with? In general, nothing to do with science, or just...
It can be, you can decide. Generally I ask this question because I want to know what's next. What are the big ideas that you're thinking about that are keeping you up at night, and where I can sort of imagine the research is going next? Okay,
so in the scientific realms of what?
No, if it's a video game you're into, or if you're really enjoying The Expanse, whatever.
Oh, The Expanse is great, but it's sort of... Well, I have to go and read the books now, because now the series has stopped for the time being. I just pick up. I hear they're very similar. So one thing, I'll say a few things. I'm obsessed with science fiction, unsurprisingly. I love to read it and watch it and write it, actually. So that's like before I was a scientist, I always thought, I'd love to be a science fiction writer, and I've kept it going. So I self-published some stuff. Doing it professionally, like getting an agent and doing everything, is really hard. But I just finished a novel like a few days ago. So I find time to keep that going. And I find that's a fun kind of liberating thing, because when you're doing science for real, you have to stay within the evidence. And you're limited by the evidence.
And the pesky laws of physics.
Exactly. Yeah. You can't just go mental. I mean, with Origins of Life, because there's less evidence, you can be a bit more imaginative in some ways. But great thing with science fiction is you can just think about any scenario and explore it, and that's really fun. I'm obsessed with tennis. My whole family is massive tennis fans, so I'm very sad. I don't know if you follow tennis at all, but Andy Murray, he's the Scottish hero that I've followed like for my whole life. He's about to retire, so I need to find a new tennis obsession there. But scientifically, the thing I'm really most excited about at the moment is something I've basically been working on for 10 years. 10 years. Also meteorites. Basically, my first ever official science project that I started with this meteorite Chelyabinsk. I wanted to come up with a way to figure out when it had engaged in a massive collision. Because you look at this rock and it's just immediately obvious. It's full of these melt veins that tell you that at some point in space it was smacked into. And what's really curious is if you look at all the rocks similar to it, the evidence as it stood back then was they all have the same age, which is freaky, because you might think there's been a bunch of collisions happening over time. And these are all different meteorites. And people hinted at the time that maybe there was some really catastrophic event that happened just before or around when the Earth formed, that like reshaped the solar system. But there wasn't confidence in the dating of this event, and the interpretation and the statistics were very low. And I kind of made it my mission to fix that problem. And I had a lot of resistance to the whole thing, but with some support from key people, we've made a lot of progress on that. And we're now confident in the ages. We've made a bunch of predictions that have been validated, followed the scientific method. We've been very confident now. And I'm literally in the process, like my meteorite's being analyzed as we speak in a something called a secondary ionization mass spectrometer. It's very expensive, so you've got to apply for the funding and convince everyone this is worth doing. And we're going to find out basically in the coming weeks whether or not I'm right and whether or not those other people were right, that the meteorites are telling us that like everything went crazy 4.45 billion years ago. And my gut instinct is that it's going to be evidence of something called the giant planet instability, where basically our astronomy models tell us that you can't make Earth, Mars, Venus, current architecture of the solar system unless Jupiter moves towards the sun, goes back out again, and in the process just completely blows away the asteroid belt, causes basically Theia to crash into the Earth, and then you end up with the current architecture. And that process should cause a bunch of collisions. It should show up in the meteorite record. And it would be a really fundamental kind of confidence-boosting result in our whole understanding of why the Earth is where it is, and has the moon, how everything is the way it is. I think it'd be a really, really nice thing to have confidence in. And we'll see if that pans out.
Well, good luck. Let me know if it pans out. Craig, thank you so much for taking the time to chat with me today. It was a lot of fun, and good luck with your research.
Thank you very much. Yeah, it was a pleasure. It was really great.
I hope you enjoyed this conversation with Craig Walton. Now, I'm going to talk about some of my thoughts on the interview, but first, I'd like to thank our patrons. Thanks to Stephen Filler-Munley, Paul Rohrbach, Abe Kingston, Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Ansis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplin, Monso, George, David Giltanan, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. This interview filled in a fairly big chunk in my curiosity, and who knows if it'll all pan out in the end, but this question of how did life form? And the more conversations that I've had with researchers who have been looking into this story keeps coming up that the Earth was just awful in the beginning. It was inhospitable in terms of the kinds of material that life had to work with, the kinds of conditions that were available on the surface. And yet here we are. And so we know that life figured it out somehow. And Every possible idea that has been proposed, I find really interesting when you think about both the sources of the nutrients that are coming to Earth to be able to provide life with the raw materials, the amino acids, the chemicals that it needs. When you consider the kinds of solvents that were available at Darwin's warm little ponds, but maybe the environments around black smokers at the bottoms of the ocean. And then you think about the additional sources of energy, chemical energy. Maybe it's from lightning strikes hitting these warm little ponds. Maybe it is from lava, volcanism, geothermal energy. There's so many different sources. And like somehow when you just look at all the raw material that early planet Earth had to work with, somehow it put those in the right combinations to get life here on Earth. And it is just a fascinating question, one of the most profound questions that we can possibly ask. And I'm kind of glad that we're not getting the answer very easily. That is like a mystery that is really worth thinking about for a long time, working hard to come up with the answer. And I think when we do finally learn, maybe in the 25 years that Dr. Walton said, that we will find out that there is a satisfying answer and it's reproducible in the lab and we can go from non-life to life over and over again. That'd be amazing. I've got a couple of other interviews about abiogenesis that you should maybe check out